Today we are going to learn about limit superior and limit inferior for a bounded sequence. Take any bounded sequence and look at its tails, meaning all the terms from some point onward, forgetting the terms before it. For each tail, find its supremum, the smallest number that is greater than or equal to every term in that tail. As we move the starting point further along the sequence, these supremum values only ever decrease or stay the same, and they converge to a number we call the limit superior. For each tail, find its infimum, the largest number that is less than or equal to every term in that tail. As we move the starting point further along the sequence, these infimum values only ever increase or stay the same, and they converge to a number we call the limit inferior. Here is the key theorem. A sequence converges if and only if its limit superior equals its limit inferior, and when they are equal, that common value is the actual limit of the sequence. Let us prove this from first principles, starting with the forward direction. Suppose the sequence converges to some number, call it L. Then for any small positive gap, all terms eventually sit within that gap of L, so both the tail supremum and the tail infimum must squeeze down onto L as well. This forces the limit superior and the limit inferior to both equal L, so they are equal to each other. Now the reverse direction. Suppose the limit superior and the limit inferior are equal, and call this shared value L, since the tail infimum is always less than or equal to every term, and the tail supremum is always greater than or equal to every term. Each term of the sequence is trapped between these two tail values. As both the tail supremum and the tail infimum converge to the same value L, the sequence itself is squeezed and must also converge to L. This completes the first principle's proof. Let us now look at a genuinely different proof of the same theorem, using the monotone convergence theorem directly, rather than an epsilon-based squeeze argument. The tail supremum sequence is decreasing and bounded below, so by the monotone convergence theorem it converges automatically, and likewise the tail infimum sequence is increasing and bounded above, so it also converges automatically. This route skips checking closeness conditions by hand and instead leans entirely on the general fact that bounded monotone sequences always converge, then simply asks when the two resulting limits agree. Now let us work through an example. Consider the sequence (-1 to the power n times the quantity 1 plus 1 over n). When n is odd, (-1 to the power n equals (-1), so the term becomes (-1 times the quantity 1 plus 1 over n, which is a small negative number just below (-1), getting closer to (-1 as n grows. When n is even, (-1 to the power n equals 1, so the term becomes the quantity 1 plus 1 over n, which is a small positive number just above 1, getting closer to 1 as n grows. Now look at the tail supremum. Since the even terms keep approaching 1 from above, the supremum of every tail is always achieved near those even terms, so the tail supremum sequence converges to 1. This means the limit superior of the sequence is 1. Now look at the tail infimum. Since the odd terms keep approaching (-1 from below, the infimum of every tail is always achieved near those odd terms, so the tail infimum sequence converges to (-1). This means the limit inferior of the sequence is (-1). Since the limit superior equals 1 and the limit inferior equals (-1, and these two values are not equal, the theorem tells us straight away that the sequence diverges. As a check step, notice we did not need to test every possible candidate limit by hand. The even terms cluster near 1, and the odd terms cluster near (-1, so no single number can be the limit, confirming that the sequence has no overall limit.